Hello and welcome to my new video on the Euler gamma function. In this video I will talk about another function, about the beta function. And you might say, okay, why is he talking about another function while talking about the gamma function? Because until now I just talked about the basic stuff about the gamma function, and now we want to relate it to other important functions, and one important function is the beta function. And the relationship, I don't tell it yet, but it has a very nice relationship with the gamma function, and if you just stay tuned, you will see it, okay? So just sit down, take some popcorn, and enjoy the video, okay? So here we have a beta function, and this B doesn't stand for our B letter, it's the Greek letter B, so we have to say that this is the beta function of two variables, S1 and S2. Here you see the S1 and here you see the S2. Our dummy integration variable is U, and our integration boundaries are 0 and 1. Now something reminds us of the gamma function, maybe here U to the S1 minus 1. So this is very similar to the gamma function beginning, and this is something strange. We had an exponential function. Here we have something like this, okay? Now let's just look how this was derived. And actually the first kahuna in mathematics to derive this was Euler, okay? So Euler was the guy who defined the gamma function, the beta function, and as well as the zeta function. And these two importance, the upcoming two videos, are very important for understanding the stuff about the zeta function. So if you want to go ahead looking my zeta function video, so please watch these two videos in order to be able to understand the upcoming videos about the zeta function, okay? Now let's just start off. What did Euler do? Okay, Euler just wanted to multiply two gamma functions, okay? He said, okay, let's multiply a gamma function for the argument S1 and gamma function for the argument S2, and they look like this, okay? And I take two dummy variables, x and y, and I could have chosen others. I just took x and y. And now let's see, what did Euler do? Okay, in the first step he said, okay, this body here is actually nothing else but a very well-defined value, okay? So you could take this value and put it into this integral, okay? It's a constant, if you want to say it like this. If you watch it at it like gamma of S2, then you see it's a constant, and I can put it in here, okay? Now, this is the steps that we will do, but before that, we have to do some substitutions, okay? The substitutions are pretty simple. I take x and substitute with u squared, so our dx is 2u du, okay? For y, we get v squared. Our differentiation, implicit differentiation, will give us dy equals 2v dv. And if you are wondering why I write it down always like this, it's pretty simple. You imagine you differentiate this in respect to x, okay? And this will give you 1. And if you do this, then you have to add, this is the implicit differentiation, you have to add a dx. And now if you differentiate u squared, you get 2u, and then you have to write a du in the last part, okay? It's a pretty easy rule to differentiate and find the substitutions. And for this you have the same rule, so let's plug them in. So here for S1, for the first part, for the first integral, we get u to S1 minus 2. It's because we have u squared, and it will multiply everything here above with 2. We have e to the minus u squared 2u du, because this is the dx that we replaced. And here for the second integral, it's pretty symmetric to that. It's very similar to that. Not symmetric, it's actually the same, only replace u by v. Now we take the same argument as before, but before doing that, I take this 2 and this 2 and write it in front of the integral. So we have 4 times this nice integral. And now if you're wondering why we have here 2s1 minus 1, it's because I multiplied this u with this u. So this is minus 2, and this is to the first power. So we get minus 2 plus 1, and this is this. For the second integral, we have the same, and this 4 as a constant factor in front of that. Now we are doing this trick that I told you already. Maybe I'll go back. Here, this is a very well-defined value. So it's converging, it's a constant value. I can take it into the integral. Now, if you look at it now, I wrote it in front like a constant. Now, if I look at this body is constant in respect to dv. So I can push it into the integral, and now I have something that is called a double integral. Okay, I have a double boundary here from 0 to infinity, and dv du. Okay, and this is a very strange thing sometimes, but it's very powerful also. Okay, now what we are doing in the next step is I'm just sorting things out. I'm taking this v and u, writing them in front, and this body and this body I'm combining to the following: e to the minus v squared plus u squared, and we close the bracket dv du. Okay, now you might think, why did he do that? And if you are looking closely at this, this should remind you of something. This is actually, if you replace v and u in your brain, so in your imagination, by x and y, you have x squared plus y squared. And this should remind you of Pythagoras, okay? And if you are thinking about Pythagoras, you should think about the trigonometric Pythagoras. So cosinus alpha squared plus sinus alpha squared, and multiply this both terms with r squared, and you have something like polar coordinates. They are called polar coordinates because you are using only the radius and the angle, but we will see on that how this works. And now we have a very big problem here, okay, because we want to substitute the following stuff. We want to substitute v as r cosinus alpha and u by r sinus alpha. Now the big topic is this body here, dv du. How can we calculate that? There are many methods. I will do a very simple method and very geometrical method. There are more analytical methods, like using the Jordan determinant. It's a very powerful way to do this kind of substitution, and I'm just doing this, okay, the normal way by geometric stuff. And if you plug this into the above equation, you get r squared cosinus alpha squared plus r squared sinus alpha squared, and you see we have r squared common in here, and we have cosinus alpha squared plus sinus alpha squared, and this will collapse into 1. Okay, this is the big step. What we want only minus r squared here above. Okay, we want to fuse both variables into 1. Okay, now how do we do that? And the important stuff is, again, finding this dv du. Actually, this is something like an area in your coordinate system. In order to understand that, I've drawn a little ugly picture here, and you can see this is a radius. Okay, this is another radius of a circle, and imagine this this change in angle to be very, very small. Okay, infinitesimally small. And then let's look how can we calculate this strange area. Okay, and calculating it is, because it's so tiny, you can say that this is actually something like a rectangle. Okay, and in order to find a rectangle, you have to find this side and this side. Okay, and the first side that we find here is dr. It's a very small displacement in the r variable. Okay, the next part is, because of this angle is called d alpha, we want to find out this arc length. Okay, and this arc length is r d alpha. Okay, not mix it up with d alpha, because you can imagine if your radius is getting larger and larger, this arc for the same angle will get larger, so we have to multiply this with r. Okay, so we get this arc length to be r d alpha. Okay, now as we assume this area to be very infinitesimally small, we can say that this is actually a rectangle, and we can, in order to find dv du, this area, we can r d alpha dr. So this is what we write in here. So dv du, if we do the substitution, we get r d alpha dr. Now let's look at the boundaries. Because we are only looking for u and v for 0 to infinity, 0 to infinity, what we have to do is, because our r, now our r is going from 0 to infinity, and our alpha is going from 0 to pi half. Okay, so we have this part of the coordinate system is integrated, so to say. Now let's write it down, what we found out. Okay, with all the substitutions. Okay, we have the boundary for r is going from 0 to infinity. For alpha, it's going from 0 to pi half. Now we have r. Now imagine we had v squared, not v squared, but we had v to the 2s2 minus 1. So if we replace v by r cosine alpha, we have r 2s2 minus 1 cosine alpha s2 minus 1. And here the same thing for the u variable that we used. Now here, this is what I told you. If we have minus v squared plus u squared, this would collapse into r squared. And here we have replaced du dv, or dv du, by r d alpha dr. Okay, now let's just take things together. We sorted out the r parts. We have them here, all the r's. Now I think I'll have this r here also. I left it here. Then we have this cosinus, this sinus, and so forth. It's just taking parts together. I just took this r from here and put it there. If you look at it, I just took this r in front of this body here, I think, or let it back. Okay, just look at it. We have here cosinus, sinus, and this strange body here, and we will have a look at this soon. And what I'm doing in the next step is, because we have, if you look at it, the left-hand side of the integral is only are only functions of r, and this is only a function of alpha. So what can we do? We can use the trick from before and say, okay, I can just take this body, integrate it in alpha, and this will give me a finite value, and I can actually take it out of the integral. Okay, I can take it out of the integral, or better, I can take out this body out of the integral and write it here. Now what I did also was to write r2s2 minus these both bodies together, so we get r to the 2s1 plus 2s2 minus 1 is just adding these both terms. Then e to the minus r squared r dr. Okay, this looks nice, doesn't it? Now we have this body and we have this body. Now let's look what we can do. In the next step, I'm doing another step back, and I'm taking now this body, because it's a constant value, out of the integral, and I write it as two separate integrals. Okay, this is here and this is here. I hope you can follow my ideas. Now what I'm doing is I'm taking this 2, this 4, which was 2 multiplied with 2, and I'm writing it here in front of this r, and I'm writing it here in front of this integral. You will see why I'm doing that. Okay, now if we look at this stuff, what we got here, and the important part, the first for our intention is this part, because it somehow reminds us of the Gaussian integral. Okay, and we know the Gaussian integral was somehow related to the gamma function. So we can imagine that this is somehow related to the gamma function. Now already did another step. I took the 2, the common 2 here above, and just wrote it as r squared to the s1 plus s2 minus 1. And now I'm doing another substitution. I'm saying that r squared is equal to u. Again, it's another dummy variable, u, not the u that we used before. And if I differentiate this implicitly, I get, first differentiate this normally, 2r, and we have to multiply a dr here and here du. I'm just using that, and the boundaries do not change. We still have from 0 to infinity. So what we get is from 0 to infinity u, okay, because r squared is equal to u to the s1 plus s2 minus 1, e to the minus u, because r squared is equal to u. And this body here, now you see why I took the 2 into here, because it's nice. We have 2r dr, which is actually, sorry, du. Okay, now the second integral isn't changed, but now let's look at it. I already told you that this is somehow related to the gamma function, and look at it. We have u to something minus 1 multiplied with e to the minus u du, and this is actually the gamma function of s1 plus s2. Okay, very nice. And now if you remember what we had before, we multiplied gamma of s1 with gamma of s2, and this gave us this. So actually, if we look at it, if you take gamma of s1 multiplied with gamma of s2 and divide it with this, you will end up having this strange looking integral. But I will comprehend them later on. Now, this is the body that I told you, gamma 1, gamma 2, and here are these bodies. And now I divide this by gamma s1 plus s2, and you end up having this very nice formula. So if you have some integrals with sinus to some power, cosinus to some power, and from 0 to pi half, so just slam this formula on them because it's a very cool integral. Now, Euler didn't stop here. Okay, Euler said, okay, it's nice, but I want to do something else, and he just said, okay, why not take this? And he didn't do this this way. I'm just writing it this way because it's more understandable. He took one sinus from this, wrote it here, took a cosinus from here, wrote it here, and this 2, you just took this from here. Now, if you look at it, what we are ending, where we are, the sinus was reduced, the power of the sinus function or sine function was reduced by 1, and the cosine function's power was also reduced by 1 because we took a sine and a cosine out of it. Sorry, I'm always saying sinus because in German you say sinus and not sine, okay? So I hope you can still understand my thoughts, okay? Now, what am I doing, okay? If I'm looking at this, and I have 2 here and 2 here, so common 2, I can factor this out. So I have sinus alpha squared to the s1 minus 1, okay? And I'm doing this. I get u, okay? I will substitute another thing. I will say u is equal to sinus alpha squared. And if I differentiate this, on the left-hand side, I just get du. On the right-hand side, I have to use the chain rule, which is first a quadratic function. So I have 2 multiplied with sinus of alpha because the power will get reduced. It's just the power rule. And then use the chain rule to see that sinus alpha will give you cosinus alpha d alpha. Now, you see, wow, look at this body and this body. This is just du. Here we get u, okay, u to the s1 minus 1, or I just show you the below equation. And the last thing that is maybe a little bit confusing but not that hard to understand is this here, because here again we have 2 common, so we can write it as cosinus squared alpha. And you know the trigonometric Pythagoras, you can write, instead of using cosinus alpha squared, you can write 1 minus sinus alpha squared, which is just, in our case, 1 minus u. And then you have this nice looking thing. And now remember how I defined the beta function. The beta function was just this body. And this is equal to this strange gamma relationship, a gamma function relationship, that the gamma function of s1 multiplied with gamma function of s2 is equal, or over this gamma s1 plus s2 is equal to this strange looking thing. Now let's comprehend. Euler defined these 2 integrals as the beta function for s1, s2, s1, s2, and you see the one is using only u's and the other is with sinus function, and here you see the other relationship to them. So instead of working with the beta function, you could always use the gamma function instead, if you are better on that. because you actually have here everything for it, okay? And actually, why did I do this video? Because I will need this body here, this formula, for a very, very special formula called the Legendre duplication formula, which is very, very important and crucial in the videos about the zeta function, because I will just need it. I just wanted to give you a full proof of everything that is used there, so you can get a better understanding of the full Riemann zeta function and its hypothesis. Okay, I think that's it for this video. I hope you had fun. If you have questions, feel free to ask, and please subscribe, because